Good morning. I'm Peter Weide, the moderator of this tutorial. I'm very happy to introduce the next two speakers, Yan Yongbu, who has been working on tinyML, first as a principal engineer at ARM, and currently the CTO and co-founder of Edge Impulse. The second speaker is Daniel Situnayaki, who lead the embedded machine learning engineering at Edge Impulse. So there are a couple of questions already. Should we start answering first the initial questions?
Let's first do our intro and then we'll get to the questions when we get them. I looked over them quickly.
Sounds good. Go ahead.
But yeah, Peter, thanks so much. Hi, welcome. I saw a couple hundred people already in the session. It's fantastic to be here again. Unfortunately, not as fun as last year when we were actually all together in the Bay Area. That was, I mean, at least for me personally, it was such a different world at that point. Not only, COVID was not here yet, but for us as well as a company. Back then, Edge Impulse was only 4 people. It was me, Dan, and my co-founder, Zach, who were standing in our desk next to the Ada Compute, next to the sign-in table at the Ada Compute board, at the Ada Compute table. And yeah, we've grown. We're a year further. We're 25 people now, I think, give or take, which is an astonishing number, actually, if you think about it. Edge Impulse is now used by, I think, over 10,000 people, 16,000 projects, and 15 million labeled data samples already uploaded to the platform. So for us, really cool, I think, and I really want to thank everyone in the tinyML community, for being part of that. And yeah, so what Dan and I are going to do today is we are going to work with you through building an actual machine learning model, deploying that to a device. I think we sent out 250 of these boards. The Silicon Labs, I can't get it in focus. The Silicon Labs Thunderbolt Sense 2. It's a Cortex-M4F microcontroller running at 40 megahertz. It has, I think, 256 kilobytes of RAM. It has a MEMS microphone, accelerometer, and a bunch of other cool sensors. So with that device, we're going to collect some data. We're going to train a model, something a bit related to conservation. Dan will talk a little bit about the efforts that we do there. We'll deploy it back to the device, and then we'll talk through a couple of the lessons that we've learned over the last 2 years in what is actually required from building this initial model to actually deploying that at scale in industrial use cases. And that is not all, because then you might think, okay, well, now I've built my model, this is the moment to sign off. No, we're going to do one of the most scary, but I think most fun things that I've ever done at a conference at the end of this talk. And that's because we're going to, everyone here in this virtual room, we're going to be building a model together. So everyone will be able to contribute data to this model. We'll build it live, and afterwards everyone can run this on their Silicon Labs Thunderbolt Sense 2, showing how incredibly cool data collection for tinyML purposes actually can be. So yeah, Dan, could you tell a bit about what we do in conservation, a bit about Elephant Edge, and about the use case that we're going to be building today?
Yeah, absolutely. So hi, everyone. My name's Dan, and I'm the founding tinyML engineer at Edge Impulse. And one of the things that's been really, amazing about this last year is we started out and we built some really cool tools that pretty much anyone can use to build and train and deploy ML models on embedded devices. And we didn't necessarily know who was going to be picking this stuff up. Like we had our ideas of where this would be useful. And one of the unexpected places that turns out is the perfect fit for embedded machine learning is conservation. And if you think about what is the sweet spot, like why would you even want to do embedded machine learning in the first place? Often there's this case where you are concerned about needing to run stuff on a small device to save energy. The whole reason you're thinking about using an embedded device is that maybe energy is a constraint. Also, for a lot of the time, one of the big advantages of embedded devices is that they're out there somewhere operating away from infrastructure, away from power for sure, but also connectivity. So you don't necessarily have this big high bandwidth connection back to a server where you'd traditionally be able to run an ML model. And it turns out like a sweet spot for this type of thing is in conservation, because you've got these types of applications where you're trying to keep track of a piece of the environment or an animal or a plant or some ecosystem that it's really important to be able to measure, to be able to understand how it's behaving, how it's changing, how humans are impacting it, or how we can better protect it. And the people who are working in this space, they're very literate about using embedded devices and deploying things like microphones to capture data in the field. There are even some decent data sets available for some of this stuff, whether it's like audio of different animals or accelerometers being used to understand the movement that particular animals are doing and understand their behavior. So what we've found is that edge impulses allow people to be able to take their domain knowledge in conservation and their expertise around animals or environments and capture some of that in the form of a model that they train and an application that they build that deploys a little bit of their understanding to the edge, so it can better keep track of what's going on at an expert level in the field. So one of the really cool things we were able to do is we got a few companies together and launched this project called Elephant Edge, and essentially we were able to. There's a company called Ernas that's developed this platform with a neck brace thing, a collar that goes around an elephant with a bunch of sensors on, and we were able to launch this challenge where we had developers in our community use or train their own models that would potentially run on this collar around an elephant's neck and help understand the elephant's behavior. And part of that, why that is really important, is because elephants live increasingly close to humans. Human settlements have expanded. Often elephants are coming onto agricultural land or even urban settings, and there can be some conflict between elephants and people, which usually ends up, pretty bad for the elephants. And if we're trying to protect elephants, it's really important to understand their behavior, what type of things they're doing, and the way that human and elephant behavior interacts. And so the Elephant Edge project resulted in a whole bunch of submissions where people were basically training models that analyze elephant behavior, sometimes using stand-ins for elephants. We had one really awesome submission where he put a collar around his dog, a really cute little pug, and trained a model to understand elephant behavior with the pug as a stand-in for the elephant. There are also folks using imaging, using cameras to be able to understand what these creatures are doing. And it has a very real impact. This kind of technology allows people who are looking at the behavior of these animals to understand what they're doing better. And it's another tool in the arsenal of the scientists who are trying to better understand our world so that they can protect it. So today we have a little bit of a similar project that we're going to be working on together. So we don't have a lot of elephants here in Montana, where I live right now. We do have a bunch of deer. But we are going to be training a model which can help discern between the footsteps of an approaching elephant and maybe of something a little bit less likely to damage your house, which is a gazelle. And to simulate our two species here, I think Jan can do a good demonstration of the footsteps of one and the other.
Absolutely. So I hope you guys can hear it. I have a microphone standing right here on my desk, so I think this should be okay. So yeah, the idea about orientation and stuff, as Dan said, I don't want everyone to leave their computer here either and look for elephants in your room, but rather we're going to be using the accelerometer in the Thunderbolt Sense 2 board. We're just going to place it flat in a central location, and you will be the elephant, and you'll be the gazelle, and you will be, well, everything else. I mean, the jungles or the savannah is a really big place, and there's much more going on than just gazelles and elephants. So let me demonstrate the gazelle. I don't know how clear that is, but it's
It's
Can you
pretty
hear it now?
quiet. It's pretty quiet. Let me see if I can
think
do it. Can you hear it from me?
anyway, so yeah, this is something you can quickly test yourself. So at least my Gazelle legs are two pens that tap quickly over my desk swiftly and nice. Whereas the elephant, of course, you know, much bigger. A bit slower, stronger stride.
And so we can't hear much of the sound through the AirPods, but Jan's banging his fists on the desk for the elephants and tapping his pens on the desk. And the key thing is what we're picking up here isn't the sound, it's the vibration. The accelerometer in our Thunderboard is going to be picking up the difference between the amount of vibration and the pattern of vibration for these two different animals that we're simulating.
Indeed. So yeah, let's actually get to it. So if you don't have a Thunderboard Sense 2 board, don't worry.
I couldn't quite hear you.
Oh.
Sorry,
that's just Siri.
Siri.
I love live demos. So if you don't have Thunderboard Sense 2 board, no problem. You can actually use your phone and even deploy this model back to your phone to try this out. So,
and while we're going, are there any questions on what we talked about so far and what we're going to be doing?
Yeah, actually, there are quite a question already, even before started, actually, the tutorial.
Excellent.
So let me ask, like, the first question is like, can I run more than one tinyML model on the same MCU?
Good question. So yeah, you can. We're not 100% set up for it at the moment in Edge Impulse, but there's nothing stopping you. So we generate your model, basically a source code. As long as you prefix that source code with model 1 or model 2, you can run it on the same MCU. And if you have an RTOS, you can even run two models in two different threads. So really running them in one go. So really cool stuff. Before you continue, Peter, if you're currently on track, go to this URL because this contains the workbook with a couple of things. So make a screenshot of this or open it right now in your browser. And after we finish this part of Q&A, we're gonna walk through this. We're gonna walk through this together.
Sounds good. The next question would be, is there an object detection feature on Edge Impulse?
That's a good question.
Excellent question. So I saw that question, fortunately, already. So today we do not, but here is a screenshot of the work that we're currently doing. This is the first object detection model that I trained end-to-end in Edge Impulse with my son. So this is coming very, very soon to an Edge Impulse instance near you.
Exciting stuff.
Very.
The next question would be, how do we get to the sweet spots where we are making models small but at the same time maintaining the high accuracy? What techniques do we employ?
I think this is a good question for Dan.
Yeah, so there's a whole load of things, you know. So I think part of it is just approaching. When you're thinking about training models, there's certain amounts of stuff that you have to do just to make sure you have good accuracy to begin with. So having a good data set is really important. Making sure you have sufficient data that represents the kind of conditions you're going to actually see in the field. And it's especially important when you're thinking about embedded, because you're often going to have less control over the environment with an embedded deployment that you would if you're sort of in a more controlled space. If you're creating a sensor that's getting deployed around an elephant's neck, you don't know necessarily where the elephant is hanging out, what the elephant's doing. So it's really important to use your kind of domain expertise to build a really good data set. Once you have that, you got to think about the evaluation metrics that you're using to understand if your model's working well, because then you couldn't compare whether a big model is working better than a small model unless you're doing some good validation. So you have to come up with some test data and some test scenarios that you're going to be trying your model out in and making sure that it works in the way that you think. And then once you've got that down, then generally our recommendation is, so within Edge Impulse, we try and choose like sensible default settings. So we will give you a suggested model architecture that is small to begin with. And you can try that out and see how it's working. And hopefully you'll get some good results with a larger architecture quite easily. And then if you want to make it smaller, what you need to do, there's kind of two sides. One side is architecturally. So you're actually making the model smaller, less neurons, less layers, less complexity. And you can essentially just have an iterative process. So you can chip away, remove some neurons, remove some layers, simplify the model, see how it impacts performance, look at what the performance is like. And we have some tools in Edge Impulse that make that really easy. You can create a version of a model. So you can train a larger model that works well, save that, and then create a bunch of versions of it that customize it slightly to make it smaller. And you'll find the sweet spot yourself. And if you start to run into issues, there are some methods you can use. You can do things like adding dropout or regularization, which adds some error to the model during training, which can help make it more robust. You can do things like data augmentation, which does some similar stuff. It kind of varies the inputs in a way that makes the model more robust. But then there's another whole side of things with optimization. So you can do things like quantize the model, where you reduce the precision of the weights, and quantization can have an impact on the model and make it less accurate. Sometimes it makes it more accurate, just if the numbers fall in the right way. But in Edge Impulse, again, we automatically create a quantized version and a non-quantized version of the model, and we give you the tools to compare them. So you can see really easily at a glance what the type of degradation is, and then there's some things you can do to reduce the impact of that degradation. So it's an iterative process of finding your own sweet spot, because only you really know how accurate the model needs to be. Everyone would like to have a model that's 99% accurate, but realistically, for most applications, you're going to be able to get really useful information out of the model, even if it's not 99% accurate. You're going to have a signal that you didn't have before. And so it's kind of up to you where that sweet spot lies.
And one of the things actually that we're going to be demonstrating in a second. If it's okay, Peter, I want to continue for now. We can do Q&A a little bit later again.
Sounds good.
But one of the things I actually show, so the model that we trained here on my desk is maybe 90% accurate, but we have tricks to kind of smooth over the results of a neural network as well, because that's something you don't want to trust literally every conclusion that you get out of it. The neural network is going to get something wrong at some point. So yeah, let's actually dive into that. So if you click that link or open it here, you will be presented with this screen. So we made a base project. It's a cool new feature actually in Edge Impulse. Let me open a new tab where we can share a complete project with the whole world. So this will not only show a data set like you might do in Kaggle, it will actually show you the complete configuration, all the neural network parameters that you had, accuracies over training, validation, and testing set, and people can clone it quickly. So you click the clone this project button, you give it a name. This will then load the stuff up, and about a minute later, you will have this same project with all the data to be able to modifiable. So I've already done that here. So that's what I'm going to be working with. So the next thing is that we want to connect our Silicon Labs board to Edge Impulse or your phone. So for the Silicon Labs board, there is the download the latest Edge Impulse firmware button here in the documentation. This is linked from the workbook. This gives you a bin file, so you just save it, and then you drag this file onto the TB004 mass storage device, like a USB drive. So I drag it.
So when you plug this thing in to your machine, it's going to show up as a USB mass storage.
Yeah. So once we drag that over, it will flash the inner firmware, and then you're basically set. For this, you'll need the Edge Impulse CLI to connect. And what that does is we use the wire to connect this board to Edge Impulse, and then we can sample data straight from there. So there's a little daemon running on your computer that then connects this board to Edge Impulse to do something useful. And to start that up, I already had it. You just run Edge Impulse daemon. And there we go. My device is now connected to the project tinyML Summit 2021. I think Dan will do the same.
Yep.
And we have 2 connected devices here. If you don't have one of these boards, you can click the button, connect a new device, use your mobile phone, click that link, and cool, now my phone is connected as a sensor. So after that, you lay down the dev board or your phone on your desk, and now we're ready to collect some data. So we have 2 animals that we want to capture data from. So let's actually start with the gazelle. Let's actually see if we have data in the right format. Make sure to set 100 hertz then. Oh, that is my phone. So let's see. I'll add 10 seconds of gazelle data. So place the sensor on a flat surface. Keep it in the same position because we're going to be collecting data in the same way. And I'm just going to do some gazelle. You can't hear this, but very vividly mimicking a gazelle.
One thing I wanted to note while Young collects this data is if you were having any issue dragging that binary onto the mass storage device, try and reset your board. So if you ran into any problem there where it just quickly sort of flashed on there and didn't, or quickly popped something up, but then it didn't seem to do very much, try resetting the board and that might help. The LEDs should flash on the board when it's happening.
For good. Yeah, and if you have any questions or something that doesn't go right, there's a link to our forum in the workbook, and we have our user success people monitoring that. So if you need quick help, that is probably faster than doing the Q&A because we can't really help you debuggers right now. So that's cool. We have a gazelle, and let's add some elephant as well here. Did I add it in the right? No. Data in the wrong frequency. Why is that bad then?
So yeah, it's a good question. So we've got the sample rate that you collect data at on a device. That can vary depending on the sensor or just what you happen to want to collect it at. And when we for training a model, we take a data set as input, and then we run the data through some signal processing and feed the output of that into our model. And we want to have a standard frequency for the data that's coming into that chain, because otherwise there's going to be this sort of difference in the output between those particular features that isn't down to something that's actually relevant in the data. It's actually just a kind of artifact of the sample rate. So it's important to make sure we have that standardized within our data set.
Cool. So we have the gazelle data now at 100 hertz. Now let me add some elephants.
So yeah, we can't hear the elephant sound, but we can see the vibration. So hopefully the accelerometer is picking that up too.
There we go. A bit slower, much more movement actually than what we see with the gazelle. A lot more subtle, small movement. This is some data I collected yesterday. So we have elephant and gazelle data, but there's one class missing, and that is not an elephant nor a gazelle. So why is that? Then shower us with your wisdom on why that is important.
So imagine, right, you've got a model trained, and the model can either determine if something is an elephant or a gazelle. That sounds great, right? So we've got this device sitting out in the field, and an elephant stomps past, and it says, hey, an elephant is here. And then a gazelle comes running past and it says, hey, a gazelle is here. But what happens when there is neither an elephant nor a gazelle there? The model only knows about elephants and gazelles. It doesn't know what not an elephant and not a gazelle looks like. So it's going to try and shoehorn any input into one of those categories. And sometimes that's okay, you know, if you had a situation where there was either something happening or not something happening, and you only had two. But in our case, we want to be able to determine whether an elephant is coming past, whether a gazelle is coming past, or whether nothing is happening. And so that's why we need this third class, which is idle, because otherwise the model has no way of expressing, hey, nothing is happening. When the model outputs a result, it basically gives us three probabilities. It'll give us the probability of it being an elephant, the probability of it being a gazelle, and the probability of it being idle. And our idle class is trained on data with the sensor just sitting there, not being banged around, just sitting on the desk, picking up the ambient vibration.
Yeah, not necessarily nothing is going on, right? So here you see a little peak, and that was because I put my coffee cup on the table, right? It's just normal standard behavior. And this is something you see in lots of problems. Like if you have audio data and you want to train on let's say a keyword, I want to know if someone says Jan or Daniel. I also want to have lots of other samples in my data set of people neither saying Jan or Daniel, because otherwise the model will trigger constantly. So cool, we have a data set. I hope everyone managed to collect some data and add it here. So from there, we are going to process this data into something that a ML model actually can learn. So there we go. So how we see this in Edge Impulse, so I'm not an ML engineer. I'm an embedded engineer who managed to find themselves in the field of ML because I think it's a useful tool for embedded engineers to help understand the world. So for me, one of the complicated parts of this is that I still have a very hard time explaining and understanding actual neural networks because you throw lots of data in. There's something going on where it finds a mathematical formula to best map this input to something output. But what happens underneath is really hard to explain. And if you're building an industrial system or something that needs to go in hundreds of thousands of devices, you want to kind of minimize the amount of black box that you ship because it's really hard to validate this kind of thing. So kind of the first step that we always do is that we say, well, how far can we actually go with signal processing? Just standard signal processing techniques, like looking at the frequency domain of the signal, looking at the total amount of energy in the signal. If you want to clean up data, what can we do with filters rather than having the neural network trying to denoise the signal? We can just apply a simple low-pass filter to do that. Or for audio signals, how can we build let's say, a spectrogram of this data? And then that typically cleans up the data, and it has a really nice benefit of making the amount of data a lot smaller. So it takes a lot less time for a neural network to learn something about it, and the network can be a lot smaller. So typically, if you look at both audio or vibration use cases, we spend about 90% of all our processing time on device in signal processing and only 10% on device, which I really like. It's a lot more explainable. So here I'll first cut up my data. So I think here that I need 1.2 seconds of data to classify. We can set this to a longer window, but it also means that you need to sample longer before you can actually classify what is happening. As we have collected samples that are 10 to 20 seconds long, we'll use a sliding window to go over this data with a step of 80 milliseconds. And then we'll have a spectral analysis block, which is one of our standard pre-processing blocks that work really well for this type of data. And then we'll have a classifier that will either say elephant, gazelle, or idle. And there's another block that is there actually in your projects. I've removed it for now because I want to show why we have that block. So as you can see in like the idle stuff, there's a lot of ambient noise happening right here. And that kind of noise we want to get rid of that as much as possible. So here you see if I don't apply a filter, there's lots of noise in this signal. But that's this kind of stuff that I don't want to see in my final result because it doesn't add anything. It's just the ambient noise. So we can say you want to apply a low pass filter, just a standard signal processing technique. And now my data set is a lot cleaner. And that's a very cheap way of doing some filtering here. After that, I want to look at the frequency domain because both my Gazelle and my elephant have some kind of, there's a time and frequency component, right? The elephant is walking like that. The Gazelle is walking a little bit faster, but with a lot less energy. So that's something I want to look at, and that's a spectral power. So if you look at a Gazelle, it's a nice bit of spectral power here. So it goes a little bit faster. So about 2 Hertz, so about 2 times per second, it does something. If I look at one of my elephants that I collected, it's a lot more, there's a nice one peak here where I do a slap, but the things you can actually get from here is that there's a lot more energy in the signal. And we have this for lots and lots of blocks. So we help you design it, or if you have something already yourself, you can just plug that into Edge Impulse as well.
So the cool thing here is that in addition to doing this during training, when you deploy your model with Edge Impulse, we build an SDK which implements this in front of your model. So you just pass in the raw signal from your sensor, and we will do all of this signal processing using whatever features are available on the processor that you're using. So that's another really cool thing about doing this in signal processing rather than saying, oh, the neural network should do all of this work, is we're able to use features of the chip that can accelerate some of this. And that helps save even more time and energy.
Yeah, so one of the things, I have a good sample here, not so much on this one. But yeah, these type of things like frequency domain analysis are stuff that is typically already implemented in silicon. So we can do this incredibly fast here. So really cool. So with all that, let's actually generate features. So we'll go over the 4.5 minutes of data that I collected. You see my previous example here already. And run this feature extraction step over all of that. And then we'll plot this data here in a graph. So as you can see, kind of what we expect. So this is the total energy in the signal on the X, Y, and Z axes. As you can see, we already see there's barely any energy in the signal here under idle. There's a lot more in Gazelle, and then there's even more for the elephant. Not necessarily there's a super clear distinction or a completely clean distinction, right? There's this place where I put my coffee mug on the table that looks suspiciously like an elephant. So we need to we can't trust just a single frame of data here and say, oh, this was an elephant, so definitely an elephant here. We still want to do some smoothing over this, run this continuously, and only if we've seen an elephant for the last, if we actually seen elephant for the last 3 seconds continuously, that is the moment that we probably want to classify as such. So that's some of the considerations here. A neural network is great, but it doesn't always give you the full picture. And that's something we've been combating quite a bit. But in general, this looks pretty cool, right? There's nice separation, not perfect, but pretty decent. So we can expect to have pretty decent accuracy actually coming from this. So let's go to our neural network classifier. As Daniel said at the beginning of the talk, we try to load a neural network architecture that just works for most people. So in this case, we loaded a fully connected network, pretty small one. If you have audio data, we probably load a convolutional neural network, etc. We will always give you full freedom in actually modifying this. So if you want an extra layer, add an extra layer. If you want to remove it again. Or if you know exactly what you're doing, you can switch to the Keras mode, and we'll give you full access to the Keras API. So if you want to implement a different loss function, if you want to do weird model architectures, you can just code this out in Keras and load that straight into Edge Impulse, which I think is really cool. Or if you want to try something out locally, just add it as an IPython notebook, open it in your favorite editor, and we'll automatically pull in the data from Edge Impulse, and you can run the training wherever you want, in SageMaker or local. Cool. So let me train that. There we go. So what we now do is we kick off a job in our compute cluster, and in there we will train a neural network. So while we're training, we see these numbers, the loss, the accuracy, the validation loss, and the validation accuracy. What does that mean then?
So basically, one of the important things to do while you're training is to monitor what's going on and how well the model is fitting the data. And there are two sorts of important things to think about here. So first of all, we're feeding training data into the model. The model is then creating an output. So the model's trying to classify each sample. Is this an elephant? Is it a gazelle? Or is it idle? And to begin with, it's going to do it very wrong. And it's just going to give essentially random outputs. And what we're trying to do during the training process over time is every time we run a sample through, we look at how wrong the result is, and then we update the weights of the model slightly so that the result's more likely to be correct next time. And over loads and loads of iterations, that leads to a model being trained. The thing is, you can't just look at whether the model is getting it right with the training data, because the training data is what the model's seen already. And something can happen called overfitting, where the model basically figures out some tricks or ways to memorize the training data exactly so it can get it right. But in reality, it's just taking some shortcuts. And if you were to show it data it hasn't seen before, it won't perform well. And so when you look at these stats here, we've got our loss and accuracy. The loss says how wrong the model is currently. The accuracy says how many of the samples that were fed through it got right. And the validation loss, and so those are on the training data. And then we have validation loss and validation accuracy. And those are on a little subset of data that we kind of keep to the side. We don't feed it into the model during the training process. The model's weights aren't based on that. But every epoch, which is sort of every iteration of doing this process, we feed through the validation data and see how well the model is performing on that. So it's important to try and make sure that your validation accuracy is good, because that's the important one. That's the one that reflects whether the model can understand data it hasn't seen before and not just data that it was trained with.
Yeah. So the model is now done. And so we show the accuracy and the loss and a confusion matrix that actually tells us like which of these classes did work very well and where got the model confused. So we see that elephant, that does really well, 94.5% accuracy and a 0.92 F1 score. Gazelle and idle, sometimes there's a bit of confusion, right? And it could very well be. Gazelle's movement is very, very soft spoken, so might be a bit the same. But one question I have now then, so we see here the validation loss is 0.22, and here the loss is 0.37, and the accuracy here was 0.91, and now it's 83. Where does that mismatch come from?
Yeah, so there's a couple of things at work there. So first of all, when we train the model, you choose how long to train for. Here we're training 60 epochs, which means we run the whole data set through 60 times. And what we do, rather than having you have to figure out the exact fiddly number of cycles that will result in the best model, because sometimes the model gets better, then it starts getting worse again. First of all, we'll automatically find the best model that was produced during training according to the validation data set. And that will be the one that you get at the end of the process. And then the second thing is, once we've trained the model, we will apply some optimizations. One of the optimizations we apply is quantization. And so like I mentioned earlier, this is where you're reducing the precision of the numbers in the model. So you're going from a floaty 32-bit representation of this number down to a compressed 8-bit version, which hopefully approximates that value quite closely, but there is some degradation there. And so what you can see in this UI here, Jan's able to switch between the unoptimized version and the optimized version, and we can see that the accuracy goes down a bit with the optimized version, which, that might not be acceptable. In this case, it probably is, because it's only a couple of percent. But the key thing to look at is if we scroll down a little bit and compare the size of the model for each and how long it will take to run. Because
Yeah. So we have, so that's the interesting part, right? If we quantize, we can do stuff. It doesn't matter too much here because the model is so small, but we are about 3 times as fast. And we use use a little bit less ROM and a little bit less RAM. However, if you look at larger models, like an audio model, this could sometimes be 3 times as little RAM, and 3 or 4 times as fast actually to run, which might very well be the consideration between, yeah, now I can actually run it on device, or now I can't run it on device because it doesn't hit my constraints.
Exactly. Yeah, embedded ML is all about managing trade-offs, and you are the only person who knows your trade-offs. You're trying to deploy this onto a device with an application. Only you know how big that application is. Only you know how important latency is, or the difference between using more ROM or RAM. And so we give you all the tools to be able to look through and compare the model performance with all of these different options and pick the one that works for you.
And one of the cool things here is actually, if you want to look at your data set and see like which one of these actually are wrong, that's something you don't really see because you get the score. It's like, yeah, 94% correct, but which ones were incorrect? You get the feature explorer here again. There's your whole training set. And you can just zoom in to every single one of these samples and see which one was misclassified. So the one where I put my coffee cup down, that indeed looks like my mouse is dying. The demo gods. So here, my coffee cup down. Okay, so that was that high. We kind of expected that was going to be classified incorrectly. And then we have lots of kind of stuff here in the middle between idle and Gazelle. So here we have Gazelle, but there's barely anything happening. Here we have idle, but there's a little bit of bump here. So we'll give you insight in your dataset quality. And very often we find actually issues with datasets here. So audio samples that are just noise, for example, because they're incorrectly cut. It's really, really quick to see this here. Cool. So we have a model and we think this is going to work. I hope I get my mouse back now. Let me actually try this out on the device. So you can go to, if you still have your device connected, you can go to live classification. And will show up here. And what you can now do is just do a bit of the movement, and it will capture the data and then classify that and tell you. So this doesn't run on device yet, but it's just a quick way of validating what's happening. So
Jan, how does this work? How is the data getting from the device into Edge Impulse?
Yeah, so you see the little daemon run here. So whenever someone clicks the button, we send a message to your computer. We say, hey, we want to get data from the accelerometer this long at this frequency. And then the device gets the instruction. The device gets the data from the sensor, and then it sends it back through this little daemon, and then we show it in the device. So let me actually redo this with the device actually laying still on my desk instead of me moving it around. All right, so I did a bit of Gazelle here. And yeah, the model actually classifies it mostly as Gazelle. There's a couple of places where it thinks it's idle, 3 frames, but 45 of these frames were classified as Gazelle, which is great, what I was doing. So we have something that, at least at first glance, looks like it works pretty well. Now, there's one place where ML models perform really, really poorly, and that is when they deal with data that I've never seen before at all. Like, it's unlike anything we've ever done. We've added this idle class, but that idle class only knows when it's laying idle. What if I just pick up the sensor and go move it around? That is definitely something the model has never seen before. So, okay, it thought it was an elephant. Does this make any sense? No, of course not. But that's not something an ML model knows, right? It needs to map this either to one of these classes. So it probably chooses the direction of most movement, most energy in the signal. Oh, that's probably an elephant, something like that. but really poor. Because if someone picks up the sensor or there's lots of wind blowing and that's something you don't expect when you deploy this on the savannah, you do not want to send a bunch of rangers down to the savannah because they think there's a bunch of elephants walking about. So how can we deal with that? Well, neural networks are not the only game in town. And we have support for more things. So we can add a second block, in this case, an anomaly detection block, that will find outliers in new data. And we like to deploy this together with a neural network because this helps us determine when we cannot trust the neural network. It will tell us when something that we see is so far outside of any known data that we should not trust this data. So you can just add it in the same way. You can have multiple of these learning blocks together in a Chimpulse. I click Save. Anomaly detection, I'll add the R, Y, and Z axes. I'll train this model. And now we're going to learn normal clusters. So this is all data that looks valid. So we run a clustering algorithm over this data. And we can now use this in conjunction with the neural network to know when we're dealing with data that we should not trust. So if I go back to my previous test sample, it will still think it was elephant all the time, but we have an anomaly score that's really, really high. And in that case, we actually say, hey, we cannot trust this data. We cannot trust the neural network. This is an anomaly. We should throw this away or have someone look at this data, actually. And that's really key, I think, for deploying neural networks in the field. Anything to add there, Dan?
Yeah, so this problem is this idea of out of distribution detection. And essentially, the idea is that your training data captures everything that you thought you'd know about before you train the model. But in the real world, there are always going to be things that come up that you don't expect. And it's natural. First of all, there's this idea of model drift, which is that if you imagine you've got a model that's looking out for particular conditions, and then the conditions in the environment change over time, whether that's like out in the field in a conservation application, or something that's looking at like consumer behavior in a supermarket or something like that. The way people behave varies year to year, day to day, month to month. So it's a really important part of any process of training and deploying and managing and supporting machine learning deployment, that you're able to understand when things have drifted from what you trained the model with. So these kinds of tools are really powerful because they give you that insight and they let you understand. Maybe if you start getting reports back from your sensor that there are a ton of anomalies, that's a good sign that you should try and capture some more training data and train a new version of your model, because obviously conditions in the field have changed. Oh, Jan, you've lost audio, I think.
Oh, sorry, I was muted.
You're back.
So yeah, we have something that works. Very cool. It's time to deploy this to the device. So we actually prepared a special firmware for this board, which is labeled here with the tinyML Summit logo, or well, text. So if you click that, we will take our model, or your model, all the spectral, all the signal processing code, all the machine learning code, both the neural network and the anomaly detection code, and combine it with a runner firmware that reads data live from the sensor and then prints the results out straight away. So it's a quick way of testing this kind of stuff out. And in this firmware, we've implemented a number of techniques that we use in the field to make this more robust against this type of inference. So to get that, hit the build button and then wait about 30 seconds for it to go. If you are doing this on your phone, there's a button at the bottom of on your phone. I'm going to show this on my screen here. That is me. And here is my phone. What the hell is going on? Huh? Can you still hear me, Dan?
Yeah, I can hear you.
Okay, that is really weird. I cannot share my phone while I'm also sharing. I cannot show my phone while I'm also sharing on WebEx, apparently. Okay. All right, I'm sorry about that then. So yeah, what I can show on your phone, just click down, click switch to classification mode, and you'll be presented with this. So just lay it flat on the table and just perform one of those classes, and it will tell you exactly what it was from there. But we're going to do this on the device itself. This is a bit of a downer.
Yeah, and so what's happening now is we've basically in the back end we've exported an SDK that contains the whole signal processing and training pipeline. And model pipeline.
Yeah, so what you can do in Edge Impulse, I think the really cool part of Edge Impulse is that we don't just let you train this model, but we can convert all of the code that you select, all the parameters, all the ML code, etc., to source code. The source code is open source, royalty free. So you don't need to pay us anything or even let us know if you deploy this to a device. And really easy to integrate in your own firmware. So that is if you do a C+ library. For the development boards that we fully support, here's a number of them. We can build a binary that combines a kind of a base firmware. So some of the stuff that we need to do data collection, but combine that with your model. And that gives you a super easy and quick way of collecting or of actually verifying that your model works on device. And then from there, you can turn it into a full application. So the source code for all of these boards, all these binaries, is completely available. It's in our docs hosted on GitHub. So super quick way of actually building real solutions using that. So I've built a binary here. I am going to drag that onto the board again. And then we'll have the same model, but now running it on the device, and you can see how fast it is and how well it works. Let's try it out. Yeah, if you have a board that's actually not supported here, don't worry. If you go to our docs page, there is this link, running your impulse locally, and that contains instructions to run this on literally anything under the sun. From 16-bit MCUs to Linux-based systems, etc., we support virtually everything. So I think that's really cool. So this is done. Let's run this on the board. So what we do now is we just take one sample of 1.2 seconds and analyze it. So on the device, and I said this goes really, really fast. On this device, we take 12 milliseconds to do the signal processing pipeline, and then 1 millisecond to do the classification, the neural network. And well, it's laying idly on my desk, and that's what it thinks it's doing as well, with no anomaly here. So I'm going to keep that running. That's kind of our first sanity check to see whether this works, yes or no. So let me go.
Looking good.
Gazelle, yeah. Okay, let me go. So elephants, there we go.
I love how the screen shakes when you do that.
Yeah, my camera is attached to my desk yet. But really great. Okay, so we figured, okay, for basic stuff, this works. It's really, really fast. You know, it's 14 milliseconds, 13 milliseconds to do the analysis for over a second worth of data. So it's great. You can basically be in sleep mode or in very low power mode, just get data from the accelerometer in the rest of the time. But let's see if we actually run in continuous mode. And what we then do is we have a timer. The timer collects data constantly, 100 times a second at 100 hertz. And then we have another a kind of a thread that does classification 5 times a second. So now we're going to see, instead of wait for 2 seconds, collect data for a second, wait for 2 seconds, collect data for a second, we're continuously running. And you're going to see some more info. All right, so we have idle. I'll go Gazelle. See, it will go up. And now it will transform back to idle. I'll go do elephant. and go back. However, if you've looked closely, there's a number of places where the model doesn't get it right. And that is fine, right? I mean, the model is not an almighty genie that knows everything that's happening. So for example, here, when I first started doing the elephant, it was elephant, 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 like 0.8 confidence, pretty nice. And then all of a sudden, for 3 frames, it actually switched back to Gazelle and then back to elephant again. And yeah, that just sometimes happens. So even if you're running continuous, especially if you're running continuous inferencing mode, don't trust the neural network always on its face value. So we have a couple of techniques that we use typically to work with this. So the first one, and this is all part of our SDK, so you can just use this straight away. The first one is a moving average filter. So in that case, we kind of introduce some history or some memory into the classifications. And that will smooth out these results a lot better than we see here. Here it's literally just the raw data. But we can also say, add a small rule-based system on top of the neural network that says, hey, out of the last 10 classifications, at least 7 of them should be the same. The minimum confidence should be 0.8 or something. And only if that's the case, then I want to show a conclusion. And otherwise, I want to get rid of that. And that's something we've actually implemented on this board. My normal serial daemon. These instructions are in the workbook if you want. So I can run impl smooth, and that implements a moving average filter and the smoothing over the results. So a small state machine on top of the results, and that will get rid of those kind of issues. So we'll start out, and at the beginning we don't know what we're looking at, right? It's uncertain. We don't have enough data yet. But now it's idle. We'll go. If we go to uncertain, we'll then go to Gazelle. If you have this running on your board, you'll actually see the blue LED turn on. I tried doing this in front of the webcam. Unfortunately, can't do it. But we have colors on that. And once again, cool. Now it's blue. And after that, at some point, it doesn't know what it is, and then we'll go back to idle. So a lot nice smoothing over this. And this will reduce a lot with having false positives, especially if you have kind of continuous data here.
And this is another place where your expertise comes in as the person who has domain knowledge and is building this application. So you know that an elephant isn't going to be there for 1 second. It's going to take some time to come through. So you can set the parameters of this smoothing so that it makes sense in a practical way.
Yeah, unless you have a very fast elephant. Yeah,
yeah, but maybe on a skateboard.
But yeah, that's kind of the stuff that we learn. So kind of the conclusions here. 1, never trust the neural network, or at least have some safeguards around it. I think the other is don't try to apply ML everywhere. If you currently have a control loop in your industrial system and there's a safety mechanism around that control loop, for example, to make sure you don't output too much power. It's a case with an industrial white goods manufacturer that we had. Keep that in place. You can train a ML model as well as you want, but never put more trust in the ML model than you ever did in your own control loop before. Add some smoothing, do some validation, look at false positives and false negatives on the device. Yeah, that's my main things. Dan?
Yeah, build a data set that's comprehensive. Yeah. You saw the little glitches that appear when we've got our idle data and there's stuff happening that kind of falls outside of the standard just flat line. If that kind of thing's going to be happening in the real world, it needs to be in your data set. There's stuff that you can do to work around that if it's hard to get data, but really nothing is as good as just having lots of nice data. Try and have balanced data as well. So yeah. If you've got these classes, we've got our 3 classes, elephant, gazelle, and idle. We want to have around equal amounts of data for each. If you don't have equal amounts of data for each, the least thing you can do is make sure that your test data set has equal amounts of data, because then you can evaluate whether the model is performing well, even if it doesn't have quite an equal amount of training data. But if you think about it, if you have 90% Gazelle data, 10% elephant, your model can get 90% accuracy by saying that everything is a Gazelle. So you need to make sure that the statistics are meaningful by having a nice balanced data set.
Okay, so this will conclude this part. Peter, I will use 5 minutes to ask people to do something, and then we can do some Q&A. So if you still have the workbook open, if not, go back to bit.ly EI tinyML. We're going to go to our second part, and we're going to build a keyword spotting model, an audio model with everyone in this virtual room. So we're going to be building a model that will recognize the word tinyML, because that's where we are. And for that, I need everyone's help, because as Dan said, we need a nice, varied, and balanced data set. And part of that is also finding kind of all the variations of data that we might encounter in the wild. And if you want to build a keyword spotting system, so a system that can recognize whenever someone says tinyML, we need data from a lot of different people. And hopefully we have a nice, varied set of people, both in accents, in pitch, etc., in this room. So that's why we need everyone to contribute here. So to do so, we put a QR code here, and I was hoping I could show my screen on my phone, but unfortunately I cannot. But once you scan that, you'll be redirected to a page like this. So this will say, connected to the tinyML Summit 2021 keywords. You can then press Get Started, and then start saying tinyML a number of times. Keep a bit of pause in between. After that, we will take your data, split it up in these samples, and upload it to a central location where the data from everyone in this conference talk will actually be. If you think right now, okay, well, I don't need to do this, there's lots of other people to do that, we'll need quite a bit of data to make this work. So we do need you to help here as well. The cool part is that after this is done, we're actually, the model that we train with this, I'm going to put it on here. Here. It's not there yet. At the moment, what you get is just something that doesn't work. And you can actually try it out at home. And hopefully this will work because your voice is already in there. So I'm going to do that now.
Oh, and I can see people's data is rolling in already. So that's really cool. Thank you.
tinyML.
Everybody keep doing it.
tinyML. 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 So yeah, this is this is super cool to see. So we're actually, this is data that all of you guys are providing. Really cool. I can actually play this. We're going to be publishing this whole project, including the whole data set, right after this talk. And let's actually continue a little bit because we need a bit more data.
Yeah, we got about 2 minutes of data so far. So feel free to contribute twice as well.
Yeah. Peter, if you have any questions, this would be a good moment.
Sounds good. Yeah, there are plenty of questions, so we can go for the top questions. So one of them is like about memory and power consumption in the MCUs. Any thoughts about optimizing techniques around that? Yeah,
so we try to do a lot of this already. So we, for example, load. So we actually have this page, the inference performance metrics. If people are interested in that, it's listed in our docs and our tips and tricks. And this contains actual RAM, ROM, and latency numbers on a wide variety of MCUs and a lot of typical models that we see, including keyword spotting models, gesture recognition, image models, etc. So what we try to do is, on the speed side, we load optimizations for the MCUs. So you have vector extensions, for example, on lots of ARM MCUs. We use those to run a lot faster. We'll use the FPU and things like FFT, hardware FFTs wherever possible to make your signal processing stuff run much faster. And then on the RAM and ROM side, we have our own compiler. It's called Eon. And I like I like to think of Eon as a sort of a TensorFlow Lite for microcontrollers, but then without the interpreter. So if people are familiar with TensorFlow Lite for microcontrollers, kind of the standard inferencing engine that lots of people use on MCU devices, you really see that it kind of comes from the Androids and iOS side, mobile side. So there's an interpreter, and you load a model file into that interpreter, and that runs that on device. It's pretty fast, but there's lots of overhead in that interpreter. So what we can do with Eon is actually serialize the state of the interpreter into code, and that leads to models that are about half the ROM and half the RAM of typical models. So we try to be as compact as possible. So if you want to know a bit more about like all of those and what you can kind of expect there, take a look at this page. And I think there's lots of stuff that are currently happening in the community that will make this go even lower, like sparsity in networks, etc. That we're currently seeing. There is a very long answer.
Awesome. Thanks. The next question would be like, has the edge inputs board been deployed for healthcare monitoring of rotating machines, such as turbines, from analyzing accelerator and IMU sensor data?
Yeah, absolutely. So the pipeline that we just saw is very alike what you would also see for rotating motors. So we have customers in predictive maintenance that use this. We have customers actually deploy this on as very similar to the conservation use case that deploy this in not rotating things, but typical predictive maintenance things in the field. We have a company, Iso Electro. I think we just published a case on our YouTube channel that uses a very similar pipeline to do power line monitoring for electric grid stuff. So yeah, totally possible. These are typical things that have a high amount of signal processing with small neural networks attached to that. So it works really well for us. I'm going to run through this pipeline a little bit, and then we can go back to Q&A, Peter.
Sounds good.
So yeah, we have lots of data. Really cool. I can click through it. I can listen to it. Okay, there's actually people really saying tinyML. That is always the thing that worries me, actually. I am going to revoke this QR code now, or revoke the API key. So if we look at this, we have a similar pipeline. So we have time series data, about a second window size. Now we have a spectrogram processing block rather than the spectral analysis block. So that will generate sort of a spectrogram, this one tuned for human speech. We have one for non-human speech and for machine sounds, etc. as well. So an example here is, so this was someone saying tinyML, and we get kind of the spectrogram. Here you see I don't know, actually. This one is a bit jagged. So you see tinyML kind of happening in spectrogram. Might not be super clear here, but fortunately we have the feature explorer that will help us there. So this was before the talk. So we have lots of two classes actually that we added. So that was the noise dataset and the unknown dataset. So we have background noise, and we have people saying, well, everything other than tinyML. So that's yes, no, I don't know, whatever other kind of keywords. And now we're going to be mixing in all the tinyML keywords that you guys contributed. And hopefully we'll start seeing a distinction between tinyML and between the rest of this data set. So how do we do this actually here? So what we do after we generate these spectrograms, we run a dimensionality reduction step over your data. We use UMAP. And that gives us kind of one overview, even though a spectrogram has hundreds of features. I think in this case about 650. Has hundreds of features. We can still plot this in just a 3D graph and kind of give an indication of how well this data set separates and if there's maybe any issues with the data. This actually looks super promising.
Oh, looking good, yeah.
It looks really good. You guys have done a really great job. So actually get rid of the noise. So we see a really nice separation between the green tinyML and the orange everything else cluster. There's still a couple of places where we can kind of dive in and say, okay, well, let's actually listen to that. That actually looks fine. But overall, really promising. We're pretty sure that the neural network can learn a little bit from this. So let's go to training. I'm going to click Start Training. And Dan, can you tell a little bit about what we do here with data augmentation?
Yeah, absolutely. So for some types of data, where we kind of know a little bit about what that data looks like and how it can vary, we can automatically introduce some variation during training. So essentially, it's like you're getting a slightly larger data set, a slightly more varied data set for free. And in this case, with audio data, we're able to do things like add noise to the audio. So for every single tinyML, which people have uploaded, we're going to create dozens of variations of that with different degrees of noise added. We're also able to mask time bands and mask frequency bands, which essentially like drops out some of the information that the model's getting trained on. So the model has to learn to understand that this is someone saying tinyML, even if part of it is cut out. And that helps the model just be a bit more robust and be able to cope with those types of variations in the real world. So we allow data augmentation for audio and for vision, and we're extending that all the time. And if you have your own data augmentation protocol that you want to use for your particular type of data, in our expert mode, you can just implement that as a Python function that's part of the chain. So it's super flexible, and it's a really good way to kind of make the most of a smaller data set.
Yeah, really, really cool. So this training is almost done. We're doing pretty well, actually. I think we're going up to about 94% on the validation set. Actually, even higher.
Wow.
That is really good to see. Might be a bit overfit because of that, but it looks pretty decent. Like you see the whole cluster of tinyML here on the side in dark green. And if you want to say, okay, I just want to know which ones were classified incorrect, I can just go here and like, okay. Those, in this case, this one is just background noise. So this was cut incorrectly by our set. So easy. So cool. Let's actually go to our library. Let's build it. So we enable Eon here. And what Eon does is it makes our model twice as small. So we go from 10.6K of RAM to 5.3K of RAM, which is a very significant saving. And that's something you just get for free. Just click the button and that's it. The Eon model gets deployed as source code. So you can just look at what it's doing, etc. Dan is going to do a small presentation during the award ceremony in a little bit. So I'm going to go and integrate this into the firmware of this board. So we have a base firmware, and I did a little bit of work there. So I'm going to integrate this model in there now. It's not much work, except for just dropping in the model, but I might need to do a little bit of calibration. So Peter, this is a good moment to have a Q&A question, and Dan, you can answer.
Sounds good.
Cool. So the next question is like, does Edge Impulse allow to train models for any kind of data? For example, is it possible to train models for something like electrocardiogram to look for anomalies?
Yeah, that's a great question. So you can upload literally anything. So any time series data that you can imagine, any kind of exotic sensor. We've had people using LiDAR, gas sensors, radar, pretty much anything you can think of, you can upload. We have a bunch of tools that make that easy as well. If you have existing data sets, you can connect into your data warehouse. If you have a bunch of files, we have a daemon that you can use to upload the files from your machine. And you can directly integrate with our API from your device as well. So we have the libraries available that make that easy to ingest data from any device. We also support images, two-dimensional data. So basically anything. And then the software essentially will, based on the dimensionality of the data, suggest a network architecture that will hopefully work well as a starting point. And then you can tweak and customize from there. So we already have folks who are doing the type of work with heart sensor data that the question described. There are even some community tutorials and guides on how to do that.
So, can you mention what you need to implement actually for this? Like what data conversion or custom data forwarder need to be done?
Yeah, so we have a forwarder which essentially runs on. Oh, Jan, are you saying something?
Just continue your question.
Oh yeah, cool. So the we have a bit of code that you can add to your own application, which you can use to collect data. So that's just available through our website and all of our Git repositories. We have a couple of command line tools which can be used to upload data as well, and it all just plugs in, so it works in the same way that you've just seen with the accelerometer data that we were collecting. The cool thing is that we also allow cryptographic signing of the data that you're collecting. So it's really important for data security that there's kind of this verification chain of data all the way from the device through your systems and into Edge Impulse. So the data format that we've defined allows for that signing so that you can see that a particular piece of data was uploaded by a particular device.
Cool. Right, so I built the firmware and actually pushed it now to S3. So if you want to try this out on your own board while I'm doing this, go to this link here, the tinyml 2021.bin, and that's the full binary that we should have now. Let me actually double check that right now that I pushed it to the right place. tinyml 20, yeah. So you can download that and just drag it to the TB004 directory, and then do this. tinyML. Yes. tinyML. No. tinyML.
Awesome.
Holy fuck, it worked.
That's fantastic.
That's really cool. So if you want to try this out, just drag that binary to your board, run Edge Impulse, run Impulse continuous, and that should be it.
Yeah, well done, everyone. And how much data did we end up with? That was with about 7 minutes of tinyML and 23 minutes of noise, 15 minutes of unknown. So you can get away with a bit of an unbalanced data set there. That's really cool.
Absolutely. Oh, you actually don't need to run Edge Impulse, run Impulse continuous. You just drag it onto the binary, it runs automatically. So we'll flash. And tinyML. Everyone who posts this on Twitter gets a beer next time we're face to face during the tinyML summit.
Yeah, definitely.
Yeah, indeed.
Definitely.
This was just 7 minutes of data, I think, which I think is really cool.
Yeah, the thing is when we I co-wrote the tinyML book with Pete Warden, and one of our examples in there was a similar thing where we're training a model to recognize yes or no, and the training process, it took so long. You run this thing, it takes a couple of hours on a machine with a GPU, and the process of getting that data and cutting it up is all very difficult. And then once you've got the model, you've got to jump through a bunch of things, write some application code to actually get it to run. So the thing that I appreciate about Edge Impulse is it's just tightened up that feedback loop, the iterative feedback loop that all of us as developers and engineers are familiar with. And by getting that really tight so that you can capture data easily, train a model quickly, test it out easily, you can test more, you can make sure that your application is working in the way that you want. And it's just so much quicker and so much easier than doing things by hand.
Yep, absolutely. Absolutely. And I think also, don't think of ML as a magic black box or something that stores anything. It's an engineering tool. And what we're building with Edge Impulse is also a tool for engineers. We have nice recipes and yeah, it works nicely out of the box, but this kind of feedback loop is really important. Constantly try this out in the same way as you would currently write your control loops. I think that's the best way to success. Cool. Do we have any questions, Peter?
Yes, still a couple of questions. So the next one is, can't we get the estimated power consumption the network trained? Example like peak RAM usage or ROM usage?
We could, but it's, yeah, the best bet to there is just look at the latency and then look at the peak power consumption in the data sheet of the MCU that you want to run this on. So typically what we say is that you can switch to a low power mode when you want to do data collection because you don't need lots of processing for that. And then you burst to the highest power mode the moment that you want to do run inferencing. So for the model here, we spend about 160 milliseconds per inference. We do it for 3 or 4 times a second. That's the moment that we want to jump to higher power consumption. Other than that, we can keep in low power consumption and use a DMA interrupt, for example, to get the new data. But in general, I think that ML projects can be much more efficient because you don't need to send anything to the cloud anymore, but it still costs power, right? So duty cycling, like if I only need a conclusion every minute, don't constantly be sampling, just sample once a minute and get some data and do the conclusion then, is still really important. The same way as you would deal with network activity, for example.
Yeah, this is very application specific as well. So imagine you've got a model you've trained and you want to determine whether there's rain falling based on the sound currently. Usually when it's raining, it rains for at least a few minutes. And so you probably only need to wake up and collect some data once every few minutes. You don't need to have the device constantly on, constantly collecting and running inference. Whereas if you had a device that was determining whether a bird is singing, birds usually only sing for a few seconds at a time. So maybe in that case, you do need to have a constant cycle running with inference running all the time. So it's very dependent on your particular application.
If people don't want to see the project, by the way, you can just go here. The final project will be here after the session. You can click through the whole thing, look at the data that we collected, listen to everyone else, what they said, and look at all the cool visualizations. Or just click the clone button to add more data if you want.
Yeah, and you can add your own keywords as well. If you clone the project, you can just start capturing your own data, add your own word, and probably need about the same amount of data as we have for the tinyML keyword.
Awesome. Next question would be, can we use it with any microcontroller board, or is it specific to the few selected microcontrollers?
No, you can deploy this. Yeah, so the C++ library that we output has nothing special in it. It is just mathematics and some nice wrapper functions. There's no external dependencies. As long as you have a C++ compiler, you can run this on your board. So we have customers doing this on 16-bit MCUs, on DSPs, Cortex-M, from Cortex-M0 to Cortex-M7, even on Linux boxes. So yeah, anywhere you want to run this. Naturally, it depends on the complexity of your model, right? But we try to give you an insight already in how fast it's going to run. So if your device is only 10K of RAM, well, this is not going to work. But we try to do that as early as possible and then give you some guidance on what you can do to actually make it run on the hardware that you need.
Can I combine vibration output along with the audio data for the neural network? Yeah,
I think it's a typical sensor fusion problem. So we do this in, there was an ECG question earlier. So for a customer, they do ECG with PPG data, with ECG data mixed with some other things to do sensor fusion. That's something you can do as well for audio and vibration. The only thing is there's a large discrepancy in the frequency typically between these. So you might need to think a bit about that. Dan, do you know?
Yeah, so I mean, you can essentially, you're going to want to merge this data before it gets into Edge Impulse. So you create a So if you think of audio data as this sort of time series, you might want to create kind of a two-dimensional time series where you've got both audio and you've got your accelerometer data along. You can do different things to try and fill in the gaps. So if your audio is higher frequency, maybe you just sort of have the accelerometer value be sticky, or you could fill in averages. Or there are a bunch of different ways that you can kind of backfill any of the gaps in the data. So you'd want to try a few approaches there, and then just train your model as normal. It's just a sort of time series model, looking at this two-dimensional thing. And I think over time we're going to be adding more and more features that make this type of sensor fusion easier to do fully within the product. But there are some things where you want to do a bit of data preparation outside of Edge Impulse first, and that's one of the examples there.
Next question. Does Edge Impulse have an option to train with quantized weights? I understand quantization at the moment is used only during the inference.
So I can talk about that a bit. So there are two approaches to quantization, and to quantizing a model. And the first of those, and the simplest of those, is doing post-training quantization, where you take a model that was trained using floating point numbers, you then apply quantization to the model after it has been trained, and you get a quantized model as a result. And then you pass in quantized values to that model, and you get an output which is quantized that you can dequantize and understand what the model's saying. So that's great. It works pretty well most of the time, but it can result in some degradation in accuracy because the model was trained on some weights, and with some values, and then the weights of the model after quantization are slightly different and don't really necessarily line up with what was going on during training. So you can lose a few percent of accuracy sometimes. Sometimes you can lose quite a lot. So the other approach is quantization aware training, where error is introduced during training to simulate the type of error that happens as a result of quantization, and the model learns to understand that there is this quantization error that it needs to compensate for. And we don't support that today, but that's something that's going to be coming to Edge Impulse in the relatively near future. And in that case, you'll just get a little bit better accuracy out of your model. Most of the time, unless you've got a big, complicated model, we don't see much quantization loss.
Sorry, I need to run. Dan, I'll let you close it out.
Okay, excellent. All right, thank you very much, Jan. And yeah, any more questions from Peter?
Yeah, a couple of. So any chance that Edge Impulse project will be available, importable, modifiable source code in Thunderbolt, similar that it's possible for Arduino?
So how would that? Can you ask that again? Sorry.
Yes. So any chance that Edge Impulse project will be available as a importable, modifiable source code to Thunderbolt?
So it is, yes. Yeah. So the source code that we have showed today, or the firmware that we've showed today on the Thunderboard, you can just grab that from our GitHub. If you go to github.com/edgeimpulse, and you can download that project, and you can do whatever you want with it. And then the SDK that we output from Edge Impulse is also just completely human readable. The binaries that we show are just for your convenience. It's just like a quick way we can do the compilation for you to make things even quicker. But if you want to build this code yourself and modify it yourself, that's absolutely straightforward, and it's all available open source. We really, we don't personally believe in giving people black box binaries or incomprehensible code. All of the code that we output, everything we output, you can understand. And if you have questions about any of it, let us know on the forum, and we're really happy to explain stuff.
That's very awesome to hear. The next question would be, is there TensorFlow Lite micro behind the conversion of the Keras model to the MCU code?
Yeah, so we use the TensorFlow ecosystem pretty heavily, and we also contribute back there. I actually used to work on the TensorFlow Lite team, so we've got some pretty strong connections to that team, and we use TensorFlow. We use Keras to provide the kind of high-level interface for our expert mode model training. We then use the TensorFlow Lite converter tooling to convert and quantize models, and the TensorFlow model optimization toolkit. And then the technology that we've built around Eon is based on TensorFlow Lite for microcontrollers. So we support the same kernels that TensorFlow Lite for microcontrollers does. We have all of the per silicon optimizations that have been built for TensorFlow Lite for microcontrollers also work with Eon. So we are making use of a lot of the TensorFlow open source tools, and we're regularly contributing patches and fixes, and we're actively part of that community too. If you are ever at the TensorFlow Lite for microcontrollers special interest group, which is the open source discussion group, I'll often be there hanging out. So yeah, we love TensorFlow.
Cool. What if the application is unbalanced? In other words, if you are unable to get a balanced data sets, for example, in a medical application like cancer detection.
Yeah, really good question. So I think the important thing here, sometimes you can't get balanced data, and the important thing is that your test data is balanced. So there's a distinction between your training data set and your test data set. The training data set's used during training, the model gets updated based on that data and contains information that's contained within that data. The test data set is data that you hold out at the end, and you only use it through understanding whether the model is performing correctly. So it's really important that your test data set is balanced, because then when you look at the statistics that come out of it, like accuracy, for example, you know that that's representative across all of the classes that you care about. Whereas if you had a real minority class with only a few samples, you could get like 90% accuracy, but you're actually getting all of the minority wrong if there were only 10% of the data were that minority class. So really important to make sure your test data is balanced, and then you can just experiment. So once you've got your balanced test data set, you can train a model using your unbalanced training set and see what the performance is like. If it ends up not working well, you could try taking out some of the data that's in the majority class. So try and equalize it a little bit and just try a lot of experiments. And as long as you've got this balanced test data set, then you will know that your model's performing well. The other thing to do is use techniques such as data augmentation to try and extend and make greater use of that data that you have. And if you've got specific domain knowledge about these types of things, then you can even generate your own data. So you can generate synthetic data that is similar to the real samples. This isn't something you can do in all cases, but for computer vision, for example, a lot of people have done things like generating synthetic data in video game engines, where you're creating photos that are of a simulated world, but can then be used to train a model that works in the real world. So there's a few approaches there. So I think I'm going to have to run because I'm going to be at the awards ceremony that's starting in a couple of minutes, but I'm going to be talking a bit about Eon there. So if you're interested in learning more about the Eon tuner technology that we've built, please drop in and say hello.
Cool.
Otherwise, thank you so much to everybody who's attended, and thank you so much to Peter as well for being an awesome moderator. And we hope you've had fun trying out Edge Impulse.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These three are the executive sponsors. And then followed by platinum sponsors. ETA Compute, Lattice Semiconductors, And the gold sponsors are Brain Chip Corporation, Cisco, DSP Group, H Impulse, EMSA Visual Sense, General Matter Labs, Green Waves Technologies, Hymex, Imagimob, Latent AI, Maxim Integrated, Kixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and Synsense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.